What if we flipped a coin 100 times? What is more likely? Less than 50 heads, exactly 50 heads, or more than 50 heads? Many of you would pick exactly 50 heads because that's how many you'd expect on average. However, what are the chances of flipping exactly 50? Oftentimes, when we don't know how to solve a problem, we look at smaller cases to find patterns. Say we flip a coin 4 times. What's the chance it comes up 2 heads and 2 tails? Here is a tree diagram of the outcome. Each leaf has a 1 in 16 chance of occurring, but there are 6 different orders in which there are exactly 2 heads. Therefore, the chances are 6 in 16, which is greater than 1/3, enough to call it most likely. But we can't draw a tree diagram for 100 flips. Even 6 flips is confusing. Each order has a 1 over 2 to the 100 chance of occurring, and we need to find the number of orders which have exactly 50 heads. We want to choose 50 heads from 100 flips. Remember, in combinatorics, that's equal to 100 choose 50. I'll now solve the 4-flip problem using this method to demonstrate that it holds, and since we get 6, it does work. I'll now denote this formula as n choose r because most calculators actually do this calculation for you. Solving the 100 flip problem is now simply typing numbers into the calculator, and we can see that you should not actually pick the 50 heads option as it has only an 8% chance of occurring. This is in essence the binomial distribution, and it shows up a lot when dealing with how many times a specific event occurs in repeated trials. This is the formula for the distribution. Don't let the notation scare you. The green X is how many successes, 50 heads in our previous example, we're looking for. N, shown in red, is how many trials, 100 coin flips before. P, shown in blue, is the chance of success in 1 trials, 50% chance of flipping heads, and Q, beige, is the chance of failure, 1 minus P, also 50% chance of flipping tails from before. Simply put, we multiply the chance of one specific leaf occurring by the number of leaves that have exactly X successes. The binomial distribution will only work if the following are true. Clearly defined success and failure are the only 2 options. The chance for success remains constant, and we are looking for the number of successes in a fixed number of trials. This is most likely confusing, so I'll demonstrate with an example. Imagine you were daydreaming in math class about what would happen when you multiplied pi and I when suddenly you were taken by the math gods to math prison. Guarding the prison are 50 guards, but because they're so irrational and they often imagine things, it takes 3 or more guards to convince them that you are indeed escaping. Sneaky as you are, each guard has only a 5% chance of seeing you. What are your chances to get out without being caught? Let's figure out what numbers to plug into the formula. There are 50 guards, so n is equal to 50. You escape if 0, 1, or 2 guards see you, so in this case, success being seen, and x is either 0, 1, or 2. And therefore p, the chance of a guard seeing you, is 0.05, q is 0.95. We solve for each value of x and then add them up to see our total chance to escape. There's a 7.8% chance no guards see you, 20.2% chance 1 guard sees you, and 26.1% chance that 2 guards see you. And so in total, you have a 54.1% chance of escaping.